Hey everyone, welcome to The Explainer. I'm absolutely thrilled to have you here. Today, we're jumping right in to completely demystify the foundational concepts of machine learning. We're going to explore the core architecture of these systems without getting bogged down in heavy math or, overly dense jargon. We're looking at the absolute fundamental choices an algorithm literally has to make.
So, this brings us to a really fascinating core question. How do machines actually learn to solve different problems? Well, it's kind of a trick question. As Andrea Burkhoff points out right at the start of his book, machines don't really learn in the biological sense that we humans or animals do. Think about it. If you learn a video game looking straight at a screen, you can still play it if the screen is tilted, right? But a machine usually can't do that unless it's explicitly told how. So for a machine, learning is really just about finding a highly specific mathematical formula that reliably produces a desired output when you feed it a bunch of inputs.
I absolutely love this famous quote from statistician George Box, and it really sets the tone for our whole exploration today. All models are wrong, but some are useful. When we talk about machine learning, we aren't talking about finding some flawless, perfect representation of the universe. No way. We're talking about finding the most useful mathematical path to solve a specific problem. It's all about utility, not perfection.
Okay, here's our roadmap for today. We'll start at the machine learning crossroads, then navigate three major forks in the road: classification versus regression, model-based versus instance-based, and finally, shallow versus deep learning. Then we'll wrap up by choosing the right path.
Okay, let's dive into this. Section 1, the machine learning crossroads, mapping the foundational concepts.
Moving right along to Section 2, classification versus regression. The first great divide. What exactly is the algorithm trying to predict?
First up on this divide, we have classification. Formally speaking, this is about automatically assigning a label to an unlabeled example from a finite set of classes. But simply put, it's really just about sorting things into specific, distinct buckets.
Take spam detection, for example. You've got an inbox full of emails. The classification algorithm looks at a new mystery email and has to make a choice. Does this go into the spam bucket or the glorious not spam bucket? The options are totally finite. It either gives you a direct label or a probability number that points right to that specific label.
But what if you aren't sorting things into buckets? What if you want to predict tomorrow's exact temperature, or maybe a future stock price? Well, that's regression. Instead of a discrete category, a regression model outputs a continuous target. We're talking about a specific value on a moving infinite scale.
And this brilliantly illustrates the difference. If you need a specific label, you walk the classification path. If you need a numerical target, you walk the regression path. This foundational choice literally shapes everything that follows.
All right, let's look at Section 3, model-based versus instance-based. The second great divide. How does the algorithm actually use its training data?
Once we know what we're predicting, we hit the mechanics of how. Now, the vast majority of supervised learning algorithms take this first route, model-based learning. This uses the training data to create a model with learned parameters. A great example from Burkhoff's text is a support vector machine, or SVM. The truly fascinating thing here is what happens next. Once those parameters are learned, the original training data can literally be discarded. The model has extracted the underlying mathematical rules it needs, so it doesn't need to carry around the heavy baggage of all that raw data anymore.
Conversely, we have instance-based learning. Now, this approach does not distill the data down into a set of parameters and throw the rest away. Instead, it uses the whole data set as the model itself. The classic example provided in the book is k-nearest neighbors. To predict a label, this algorithm literally looks at the close neighborhood of the input example within the vast space of all the feature vectors it has memorized. So it absolutely needs all that original data to stick around so it can compare new inputs against it.
The stark difference here is really memory. Model-based learns the rule and just forgets the examples. Instance-based, on the other hand, hoards every single specific example to figure out the rule on the fly. Just imagine the massive computational memory needed for instance-based learning if you're dealing with millions of data points. It's a huge trade-off.
Let's move to Section 4 and see how this builds. Shallow versus deep learning. The third great divide. How complex is the algorithm's architecture?
So, most traditional supervised learning algorithms fall into the category of shallow learning. I know, shallow sounds a bit like a pejorative, right? But it really just means the architecture is relatively straightforward. A shallow learning algorithm learns the parameters of the model directly from the features of the training examples you give it. There's just a direct, uncomplicated line between the input features and the learned parameters.
But then, of course, we have the ultimate buzzword of our modern era, deep learning. Deep learning refers to neural networks that have more than one layer between the input and the output. We often call these intermediary stages hidden layers. And crucially, unlike shallow learning, most model parameters here are not learned directly from the original features. Instead, they are learned from the outputs of the preceding layers.
So the crucial point is how this abstraction works in sequence. First, you input the raw initial features. Then they process through a preceding layer. Step 3 is where the magic happens. The algorithm learns its parameters from that layer's output, which is an abstracted version of the data. It compounds this understanding through multiple layers to finally get to step 4, the final deep neural network output.
Putting them side by side really highlights this incredible architectural leap. Shallow learning relies on that direct, immediate connection to the original features. Deep learning, though, embraces sequential abstraction, pulling its insights from the layers that came right before it. It's exactly this depth that allows deep neural networks to handle incredibly complex tasks like image and speech recognition.
And that brings us to Section 5, choosing the right path. Summarizing the ML toolkit,
All of these foundational concepts, straight from Andre Berkov's guide, form the essential building blocks of the AI we interact with. Whether an algorithm is doing classification to filter out your spam, or running a regression to predict your commute time, whether it's a model-based system that learned a sleek mathematical rule, or an instance-based system meticulously checking against a massive dataset. Whether it's shallow and direct, or a deep neural network processing through hidden layers, these are the definitive choices that dictate how the machine operates.
I want to leave you with this final, provocative thought. You interact with dozens of invisible algorithms every single day, from your social media feed to your bank's fraud detection. Based on what we've unpacked in this explainer, I challenge you to ask yourself, as you interact with invisible algorithms every day, which path did they take to get to your screen? Are they classifying you or running a regression on your habits? Are they shallow or deep? Thinking about these divides is the absolute key to truly understanding the technology that powers our modern world. Thanks so much for joining me today, and keep learning.